Okay, I hope you've read those notes that I put online for you already. So here's your chance to really figure out if you understand what you just read. So the package I asked you to read was about max-min problems. And I want you to, for exercise number 1, find and classify all the critical points from the following functions. Now you should remember that from single variable calculus, to find critical points, you find the first derivative, set it equals 0, and solve. Then you have to figure out if it's a max or min by using either the first derivative test or the second derivative test. Well, with multivariable calculus, you kind of do the same thing, remember? So the first step is to set the derivative equals 0. Now, which derivative are we talking about? Well, in this case, you need to find the derivative with respect to x, the partial derivative, and you also need to find the partial derivative with respect to y, and make both of them equal to 0. So, let's see how we can do this. If I did the derivative with respect to x, so once again, z can just be a function f of x comma y. So the derivative here, x is my variable, so 6x squared. Notice here, x is my variable, so my constant is actually 6y, or negative 6y. And since x is my variable, y is a constant, the derivative of 3y squared in this case is 0. Similarly, now I want to take y being the variable, so the derivative of 2x cubed, that's just 0, because it's a constant. Here we get negative 6x, and then we have plus 6y. If we set both of these things equal to 0 now, what you will see is that you get the following equations. 6x squared equals 6y, y equals to x squared. That's from the first part. And then from the second part, I think I get 6x equals 6y, or y equals to x. And now the question is, how do I solve these two equations? Yes. Remember system of equations? So now you have to take equation number 1 and number 2 and do something to it. Either add it, subtract it, I don't know, substitute, all that kind of stuff. So now what I'll say is, let's just substitute 2 into 1. And if I do that, I get x squared equals to x. And then if I were to move everything to one side, notice I can factor, and lo and behold now, I can solve for x. X equals to 0, x equals to 1, and that of course corresponds to then, therefore, y equals to 0 and y equals to 1. So really what you've just told me is that there are two critical points. So there are two critical points at 0, 0 and 1, 1. So now when we do multivariable calculus, we're going to apply the second derivative test, and then the second derivative test is what's going to tell us if this is a max or min, or something called remember, a saddle point. That's right. So use, let's say, the second derivative test. And for the second derivative test, you need to actually calculate a few more things. You need to calculate f(x), which is the second derivative of the partial derivative of x. In this case, it's just 12x. You'll need the partial derivative with respect to y, second derivative. That would just be positive 6. And then you need the cross derivative, fxy, and that would be the derivative of the x function, but now taking its derivative with y as the variable. And if you do that, you get negative 6. Okay, so once again, I'm doing this, the derivative with respect to y now. So there we go, negative 6. And then you just have to plug it into the formula. So there's a lovely formula we use. So the expression is what? F of xx times f of xy, yy minus f of xy. And in this case, for 0, 0, we have 12 times 0, and then we have 6 minus negative 6. That answer just gives us what? Positive 6 in this case, is it? Oh, I forgot a square here, my fault. F of xy squared, my apologies. This is actually negative 36. So in that's the case, that's less than 0, then by your notes, you know this is what they call a saddle point. And for the other one, for 1 comma 1, 12 times 1, 6 minus negative 6 squared. 72 minus 36, that's equal to 36. That's bigger than 0. So if it's bigger than 0, what do we see? You have to then also decide what happens to f of xx. Fxx is also bigger than 0. So because of these two things, we now can say this is a local maximum. Okay? So this is how we do max-min problems using the second derivative test for multivariable calculus. All right, so part B is the same kind of instruction, it's just a different equation or function. So I'm going to ask you to try this on your own, please. And then, like I said earlier, you come back and take a look. Remember, find the partial derivatives, make them equal to 0, solve, and then use the second derivative test. Go! By the way, some of you are thinking, Mr. Lee, can I just rewrite this? Yeah, you can. You can simplify it first, by all means. It might actually be easier for you if you do. If you don't like solving for y, I guess you could have just done it the way around too, by the way. You can substitute 1 into 2. It doesn't really matter, but I think in the previous example I solved for x, so I guess I'll do that here too. All right, did you get those two answers for x? Don't forget you should solve for y now, and if x equals to 0, I plug it back into our equation for y. I get here y equals to 1 over 0 squared. Huh? Infinity? I think, therefore, we have to kind of reject. No such point here. If I plug in negative 1/2, y equals to 1 over negative 1/2 squared. That's positive 1/4 in the denominator. 1 divided by 1/4 is 4, so that works here too. So I guess we have one critical point then. So our critical point will be the value negative 1/2 for x and 4 for y. And then now use the second derivative test to check this out to determine what it is. So here we go. What's f of xx times f of yy minus f of xy all squared? F of xx, the derivative of negative 1/2 x squared. I'm looking here right now. That would be positive 2x cubed. Fyy, the derivative there would be what? Negative 16 over y cubed. And then the cross derivative will just be 1 squared. Okay, we're going to plug in our values. 2 times negative, or divided by negative 1/2 cubed. Negative 16 4 cubed minus 1. That's an eighth, negative eighth. That's negative 16 then. Negative 16 times negative 16 over 64. That's a quarter. So that's 4 minus 1. I think this is equal to 3. And 3 in my books is bigger than 0. So that's good. It's not a saddle point. But now we have to check what fxx was. That was less than 0. So these two things combined together show that this must be a, that's right, local maximum. Good. If you got this, you understand the procedure of finding these max-min points. Cool. If they ask you for the value, by the way, then you have to plug it back in to the equation and figure what z is. That's all. Okay. Now, let's do one more example on the back side. Ooh, find the absolute maximum now. Okay. On the triangular plane. Ooh. Triangular plane bounded by x equals 0, y equals 0, and this equation y equals 9 minus x. So how do we find absolute maximums when we did single variable calculus? Yes, we found the critical points, but then afterwards we had to check the boundary conditions. So that's the same thing here. Okay, so first step here, let's take a look at the critical points, and the critical points will be the inside or interior of this plane. So we'll do the same procedures as before on the previous questions. Derivative here is 2 minus 2x. This is 2 minus 2y. Setting it equal to 0. This is nice. 2x equals to 2. 2y equals to 2. So x equals to 1. Y equals to 1. Beautiful. We have the coordinate 1, 1. Nice. Now, we can check in a second, but remember the idea is we need to find the absolute maximum. So after you found the critical points which are inside the region, so this is inside the region, we need to now look at the boundary conditions. So we need to check the boundary conditions. Now the question is, what's my boundary condition here? It's actually a plane. So if I were to draw a picture here, look like this. X equals to 0, y equals to 0, and then you have this line y equals to 9 minus x. So this is your plane, okay? And notice that your original critical point is here, 1, 1, but we need to check the boundary conditions. So the boundary conditions are, this boundary, and this boundary. So let's check our first boundary here of x equal to 0. Okay, and when I say x equals to 0, I'm also implying here that the y value has to be between 0 and 9. So I'm actually describing these boundaries right here, or this boundary. Okay? Now, when that happens, look what happens to our equation for z. Z now magically transforms into what? 2 plus, well, there's no more x, that's gone, 2y minus y squared. So I'd like us to actually find the derivative with respect to z now. Okay. And we can do that. So the z prime here, in this case, would be just 2 minus 2y. If we set this equal to 0, we get 2 equals to 2y, so y equals to 1. So one of the other potential points now is x is 0, y is 1. We should check this one here too. Okay? Now don't forget, we should also have the, I'll just keep going for now first. Okay, let's do the next boundary. What would the next boundary be? We can take this one where it's y equals to 0. Sure, y equals to 0. In that case, then the x values have to be between 0 and 9 as well. And that represents this boundary here. We will then make the substitution into our equation. Z equals to 2 plus, what is it now? 2x minus x squared. Okay. We'll do z prime again, and this time in terms of x. We will find when we set it equal to 0 that also x equals to 1, and that means we have the coordinate 1, 0. So we actually have to test this point as well, 1, 0. And then finally, the third boundary. Yes, we have 3 boundaries here. So the third boundary would be the slanted one. That's the line. Y equals to 9 minus x. And if I were to replace that into the z equation, wherever I see y, here's what you get. Z equals to 2 plus 2x plus 2y minus x squared minus y squared. Okay? And now I'm not going to expand this out because I just want to find its derivative with respect to x in this case. So 2 minus 2, right? And minus 2x. And here we can use chain rule. And then I can set this equal to 0. So let's see what that is. 2 minus 2 is 0. That's beautiful. Negative 2x minus 18. Oops, I should say plus 18. Negative, negative, negative minus 2x. So I have here 4x equals to 18. So x equals to 9 over 2. Now when I plug this back into the equation here, then the y value is 9 minus 9 over 2, which is also 9 over 2. So there's another coordinate I have to test. 9 over 2, 9 over 2. So that would be, I don't know, somewhere, let's say right about here. So look, 9 over 2, 9 over 2, 1, 1, 1, 0, 0, oops, 0, 1, and then, no, I was right. What am I doing? 1, 0, 0, 1. Okay? If you think these are the points, 1, 2, 3, 4, you are almost right. Because not only do we check these boundaries, we also need to, and this is a star here, don't forget the corners, because that's like your boundary too. So we also need to check 0, 0. We also need to check 9, 0. And we also need to check 0, 9. So we also should include these points here as well. 9, 0, 0, 0, 0, 9. 1, 2, 3, 4, 5, 6, 7 different points to check. So these are just our candidates for the absolute max. Okay? And then now you need to check. So step 3 is to actually check all possible candidates to find the absolute max. Have fun. So z equals to, what's our equation again? 2 plus 2x plus 2y minus x squared minus y squared. Plug them all in. I'll let you do that. And then if you do it, which I hope you will, I hope that you will find that, I believe, the absolute max, so fx of y, which is the z value, is I believe 4, and it occurs at 1, 1. And then your minimum, the absolute minimum value, the lowest is negative 61, and that occurs at actually 2 possible points, all of them corners, There you go. Okay. I hope this gives you a better understanding of max-min problems in multivariable calculus, but ultimately I'm hoping that you would have done all this on your own because you would have read the notes from the textbook really, really well. All right, that's it.